So far we have discussed about steady and unsteady flows typically in the low Reynolds number regime. It is also important to recognize that the kinds of flows that we have considered so far have a fixed confinement height or a fixed confinement diameter, but in reality there could be situations when the confinement height itself could be a function of position and time, and that is an interesting situation schematically represented in a way something like this. So, let us say that you have a bottom boundary where this height h is a function of x and time. H is a function of x is quite clear. It is a function of time in a sense that this gap like this could be lifted or put down, so that this gap could be driven as a function of time. So, in this scenario, so if you imagine this as a channel, this is a special type of channel flow, but the channel is not the usual channel that we are talking about. So, what could be the applications of this kind of a scenario? In engineering I have already talked about bearings. So, in engineering there is a type of bearing called as slided bearing, and there the configuration is something like this. So, this is a smooth linear function instead of such a complicated function, and but this is like a tapered geometry and not a regular parallel geometry. The other example is like if you have one plate and if you want to deposit a coating on this one, so you put in another plate or a paint brush and deposit a coating of a paint on top of this. So, as the paint brush is coming close to this and trying to deposit the pattern, so you can imagine that this boundary is coming down. Similarly, so interestingly, so this is quite intuitive that when this boundary, the top boundary comes down, there will be a resistance to it against coming further down. When it goes up, there is a resistance against it of going further up, and at the end of this chapter we will learn why that happens. So, all these physical problems fall under the paradigm of one mathematical theory which is called as lubrication theory. This has evolved from a pure mathematical theory based on asymptotic analysis, but it has been given subsequently an engineering flavor because the applications of this theory have been found to be very relevant in lubrication and bearing, which is one of the very important engineering aspects. So, we will for simplification first consider that it is a 2-dimensional problem. So, this is the x axis and you can set up the y axis in this way. Because the height h is a continuous function, it could be a discrete function also of x and time. So, you have the extreme heights and let us say the maximum height is h naught and the minimum height is h min. Length of the channel is L, and we assume for the time being that there is no difference in weightability across this surface, so that the physics remains invariant along the length L, otherwise L no more remains the characteristic length scale of the system along X. Now for this theory to work, first of all we have to understand that what are the assumptions that we are going to make to get into this theory. For the theory to work, we should have the gap height much less than the length. So this is very similar to the low Reynolds number hydrodynamics that we have studied earlier. Here the additional complexity is the variable nature of the gap. So when we say that the gap height is much less than the length, what is that characteristic height that we should consider, H minimum or H maximum? Yes, we should consider H max, because if H max is much less than L, H minimum will surely be much less than L. So the conservative parameter is H naught by L much less than 1. So this we define as a small parameter epsilon. Okay. So now we will make certain assumptions. First of all we will assume that it is an incompressible flow. So if it is an incompressible flow, and it is a 2D flow. So 2D incompressible flow, so just like many other previous problems or previous cases, what we will do is we will make an order of magnitude analysis of this. So this is of the order of some characteristic velocity by the characteristic length along X. Now the question is, what is the characteristic velocity, how is it generated? So we will complicate this problem a bit further, make it more generic by considering that okay, before that I will use a different type of symbol for solving all these problems, because we will be essentially working with non-dimensional equations. So dimensional equations I will give dimensional variables as dash. So all these we will make dash, because majority will be dimensionless equation, so it will be easy to write. So this this will have this boundary has an arbitrary velocity. So what is that velocity? Okay. So if you give this boundary an arbitrary velocity, that is how you can generate all types of very complex flows, and not only that, very complex body forces also can be present. So this is a very general class of problem that we are considering, much more general than flow through a channel or a pipe. So this is of the order of UC by L, this is of the order of right. Problem is we do not know UC, we do not know VC, because this is absolutely an arbitrary general situation which we have introduced. So, UC and VC will depend on what is the actual physics that is governing the problem. So, we cannot really commit anything on that, but what we can commit that these two terms should be of the same order, that means VC is of the order of UC into H naught by L, which is epsilon UC, that much we can say. So, if epsilon is very small, VC will be much less than UC, that much we can say. So, this might appear to be a little bit non-intuitive at times, because if this plate is imagine that instead of a curved boundary there is a plate on the top of this, which is a special case of this, and let us say that plate is given a vertical velocity. So, still given an imposed vertical velocity, do you still have this? That is the interesting question that we will address later on, that even when you impose a vertical velocity, so still will this hold? By continuity this has to hold, right. So, now we will consider the momentum equation. Because this h could be a function of x and time, and this boundary is given a velocity, with all these considerations it is quite obvious that it is likely to be an unsteady flow. So, in general most importantly, so I will give dash to all terms. I mean the general tendency is to write like this. So, first I write and then put a dash to all terms. Plus a body force per unit volume along x, say Fx dash. This is very important because this itself can change the physics of the problem, not the motion of the boundary, but let us say there is an electrical field which is driving the flow, that can alter the physics of the problem. So, we will make a scaling of various terms. So, what is the order of this term? Rho UC by TC. This is of the order of rho UC square by L, and this is of the order of rho Vc into UC by H naught. This is of the order of some Pc by L, where Pc is the characteristic pressure scale, that is the pressure difference that is existing across the x equal to 0 and x equal to L. This is of the order of mu UC by L square, and this is of the order of mu UC by H naught square, and this let us say is of the order of some Fxc. This is absolutely arbitrary, you do not know what is the force, it could be of electrical, magnetic, whatever, it could be anything. Now, if we assume, so this time scale, as we have discussed, that it could be in general be either advective or diffusive or forcing time scale for an unsteady problem, but a problem where there is no forced time dependence and diffusion is not that significant. So, there this is mostly guided by the advective time scale. So, then in that case so these two terms become of the same order, and Vc is of the order of Uc into H naught by L. Okay. So, then you can see that all the terms in the left hand side become essentially of the same order. Now, what we will do is we will introduce a new variable which is a dimensionless variable u dash by uc, v dash by vc, x dash by L, y dash by H naught, p dash by Pc, then fx is fx dash by fxc. Okay. So, by the way, this is momentum equation x momentum, right. We will also have y momentum equation, and that also may be important typically if you have a vertical motion or if you have a strong vertical force, then y momentum will be very important. So, this is not like a classical channel flow where y momentum will just give pressure gradient along y equal to 0. So, it can give something more significant than that. So, now if we write the terms with dimension dimensionless form, so it will be rho uc square by Lc, that will come out, or L rho uc square by L Okay. Now we can make some ready observations. What are the ready observations? The first observation is that this term will be much more important than this term. See, what is the purpose of this kind of non-dimensionalization? When you non-dimensionalize, you divide a particular dimensional variable with its corresponding reference dimension, but if the reference dimension happens to be the order of that variable itself, then that ratio comes out to be of the order of 1. Okay. So, for example, here you have non-dimensionalized V as V dash by Vc. So, because Vc is the corresponding scale of these, this ratio is of the order of 1, but had you non-dimensionalized V as V dash by Uc, that is also acceptable non-dimensionalization, but that is not a non-dimensionalization consistent with the scale of the problem. So, in that case there is no guarantee that it is of the order of 1. So, here we have chosen reference variables which are of the order of the scale of the physical scale of the problem, and once it is done, all these derivatives are of the order of 1. Okay. So, how these terms compete with the other will completely depend on the coefficients of the derivatives, because derivatives are already of the order of 1. So, then this ready conclusion that we can make is that out of these two terms, this one will dominate, because H naught is much less than L. So, in a most general physical situation, you might have this term itself negligible. For example, in low Reynolds number hydrodynamics, we know intuitively, and we will see here also, that this term is not important because this is the advection term. This force may be completely absent, right, and out of these two this is important, and if this has to be important, there is something else that has to balance it, and that is this pressure gradient term. So, from that we can conclude that the scale of the pressure gradient term you can equate with okay. So, from here we can say that Pc is of the order of mu uc by H0 square L. So, in terms of epsilon, Pc is of the order of mu uc, so by epsilon square L, you multiply both numerator and denominator by L. So, this becomes epsilon square. Yes. No, in every problem there will be so the pressure scale is guided by the fact that whenever you consider a situation where there is no other effect. So, of course, you could have a pressure scale which will depend on this term also, I mean which will not depend on this term, which will have some dependence on this term, but we will see soon that the dependence on this term will be of much lower order than the dependencies of these terms. I mean once we work it out we will see why. So, there will be other dependencies also on pressure, not that pressure is only dependent on that, but all those dependencies are higher order dependencies. The leading order dependence is this is of the order of this. So, if one has to do it formally, there is a formal way of doing it. Formal way is, because there is a small parameter, you write u is equal to some u naught, not same as this u naught plus epsilon u1 plus epsilon square u2. In this way, in the power series you expand, you can expand this continuous function in such a power series provided it is a small parameter. So, in this way you do V, you do P, and then if you take the leading order extract, that leading order extract will give you this. Just to save time, mathematicians do a work in a certain way, engineers and physicists tend to do the same work in a more intuitive way with less hard work, and that is what I am trying to do. So, you can of course put that u equal to this, v equal to this, p equal to this, separate various orders, but these will be the leading order effect. So, the leading order effect is this one. Now, so you can see that the pressure is quite strong because the pressure scales with 1 by epsilon square and epsilon is very small. So, pressure happens to be a very very important consideration in lubrication theory. Now, what we will do is we will multiply both sides by L by Pc. So, rho uc square by L into L by Pc So, clearly, so let us write this mu uc by L square into L by Pc okay. So, by looking into all these terms without doing any calculation, can you tell there is one term where the coefficient will be 1 other than this? What is that term? Yes, this one, because the scale was chosen so that this balances this, right. So, this will be 1, I am not doing any more calculation. So, for the others let us do a quick calculation, this is little bit of algebra but we have to do it. Rho uc square by L into L by Pc. So, this is rho uc square by Pc, Pc is mu uc into L by H naught square. So, you can write this as rho uc L by mu into H naught square, H naught by L square. So, this is Reynolds number based on L into epsilon square, okay. So, this is I am writing this as, so Reynolds number into epsilon square. Keep in mind that traditionally in lubrication theory the Reynolds number is defined based on the axial length scale. The reason is that it is something which is which is normally fixed. This one, the length scale is of course fixed, but the physical length it can vary across L. So, this will be what? Mu uc by L square into L by Pc. So, mu uc by L square into L by Pc into L by mu uc L. So, this is mu uc will get cancelled, L will get cancelled. So, this is epsilon square, okay. So, this will be epsilon square and Fxc into L by Pc is Fxc into H naught square by mu uc. So, this is H naught square by mu uc, right. So, clearly in the leading order there are couple of terms which you can easily neglect. What are those terms? The terms which are of the order of epsilon square, because your leading order term, so this is of the order of 1 the coefficient here is also of the order of 1, you are not touching the body force because you do not know what it is. So, you cannot just rule it out that it is negligible, it may be important, it may not be important. So, we are not ruling it out. So, what we can clearly rule out is this term and this term provided the Reynolds number is small. If the Reynolds number is abnormally large, then with epsilon square multiplication also it may be important. But in microfluidics we are primarily doing the low Reynolds number hydrodynamics. So, this can Reynolds number is small multiplied with epsilon square, so this can be neglected. So, the X momentum equation summarily boils down to a simplified equation, and that simplified equation is actually true in the leading order, not for the whole term, only for the leading order. So, you have 0 is equal to minus pressure gradient plus okay. This is H naught square by mu uc. So, we will stop here for the time being and we will continue with the next with this in the next lecture, when we will look into the Y momentum equation. The broad objective will be to find out a distribution of pressure between these two confining boundaries because of the complex phenomenon that is going inside, and that we will do in the next lecture. Thank you.